All right, good afternoon, ladies and gentlemen. We just entered Chapter 7 today after we finished up Chapter 6 when we started talking about 7.1, which are trig identities. Now, a lot of people who have dealt with anything trigonometric, when they deal with these identities, they really just don't know where they come from. So they think they're just a whole bunch of random formulas that people throw out and they push around. So hopefully we can dispel that and give it some sort of internal value. Um, so let me just take you back to the beginning of all this trig function stuff where we had the unit circle. Okay, if I took any, ooh, that looks terrible. Let me get a better picture here. Here's my unit circle. Okay, now if I took any point, and here's the origin on a unit circle, well, if I were to take this point, this is a point x, y that's on the circle. Now, if you remember the equation for the unit circle, it goes through the x and y axis, there it goes through the origin. The equation for this circle, if you think about it, the radius from here to here is 1. Okay, so if we were to strike a triangle onto the x-axis, this x value is this x value. This y value is this y value. So if we were to just put Pythagorean theorem together, we end up getting x squared plus y squared equals 1, which is totally anticipated. This is what you would expect the unit circle to be, because that's what we've been talking about it for the beginning of the class. Now, let's expound a little bit. Now, we already know that the cosine of this angle theta is the x, and the sine of that same angle theta is the y. So let's do some quick substitution here. So we end up getting cosine of theta, right, because that's the x, plus sine of theta squared, that's the y, has to equal 1. This is actually the first Pythagorean identity, and this is why you always see sine squared plus cosine squared equals 1. It's because this is all based off the unit circle. So this has a big name. This is called the Pythagorean identity. Okay? And why is it identity? And the reason why it's so important is because it's just Pythagorean theorem in terms of an angle, okay, which is big. It's really, really big. I want to talk about this in the way I'm writing this. You will never see it written like this. Note, and this is a big piece of notation that everyone needs to keep in mind. Otherwise, the rest of the book is going to be terrible. No one ever writes it like this. If they want to write cosine of theta squared, this is how they write it. Cosine, and the square is written as an exponent next to the cosine, and then the theta is written down. So this is what they'll actually do. So we end up having cosine squared theta plus sine squared theta equals 1. And this is your Pythagorean identity. Easy as pie, 3.14. Okay? So this is really all we need to do. Now, there are a couple ways of altering the identity to suit other trig identities. Okay, so sometimes we want to talk about things in terms of sine, secant, or cosecant, or tangent. All right, so let's explore what this means. Now, when I mean other versions, literally, I feel like this is the only one you need. Okay, but let's manipulate this a little bit and get an idea of other ways this thing could be. So let me clear this out for you. So this is the guy, and we'll keep this in our head: sine squared theta plus cosine squared theta equals 1. Okay, so we'll call that our first version of a Pythagorean identity. Okay, so let's do some manipulation here. How would I produce a tangent? So let's say I needed there was a formula like we were talking about, those triangles of incline, or excuse me, of elevation and the depression that requires tangent an awful lot. So this formula wouldn't really help too much if we don't have tangent in it. So I want you to think about this. What is tangent? Tangent is sine over cosine, correct? So check this out. I'm going to create a tangent in here by dividing all three of these guys, sine squared, cosine squared, and 1, all by not just cosine, but cosine squared. And why cosine squared? Because if this is sine squared, I'm going to need 2 of them to produce the tangent. So I'm going to divide everything by cosine of theta. Okay, and good news, Whatever I do to one side, I can do to the other side. So I'm going to do the roundabout long way so you get a full understanding of how this is all coming. Okay, so obviously this is going to be 1 sine squared theta. Well, that's just this. Cosine of theta, that's just that. And 1 over cosine squared, well, I'll write it out just so you guys can feel warm and fuzzy inside. Okay, but this is going to be, well, what is this? This is actually secant, right? The inverse of cosine is secant. So this is actually secant of theta squared. Why so? Because this is actually 1 over cosine of theta squared. Okay, I'm trying to show you all the little intricacies of it so there's no confusion. Same thing with here. When I have the same exponent, I can combine it under the same exponent. I end up getting this. Well, all right, guys. What's sine over cosine? Tangent. So another way we can use the tangent and the secant is by using the Pythagorean identity to manipulate. And this is important. If you notice when you start talking about calculus, we always talk about tangent lines that are tangent to the curve, and secant lines that cut through at 2 points. So this is a very big relationship in another version. So this is the second one. Okay, and there is one more. Unfortunately, my software doesn't allow me to erase part. I have to erase all of it. So I'll do number 3. And number 3 is going to be the exact same way. Instead of dividing by cosine, I'm actually going to divide by sine and see what I get. So here we go. I'm going to erase my board. All right, let's start with the Pythagorean identity. Theta plus cosine squared theta equals 1. Now I'm not going to do all the rewriting like I did with the last one. I think we got to get used to looking at it. So I'm going to divide everything. What did I say? Let's divide everything by we got cosine. We divided by cosine to get tangent. So let's divide everything by sine squared theta. Okay, now we simplify this all down. What we end up getting is 1 plus, all right, this is going to end up becoming cotangent squared theta. How so? Let's explore this. This is cosine of theta over sine of theta. Both of them are squared. And then I'm going to use the same method as last time. This is cosine of theta over sine of theta, all squared. And cosine over sine is cotangent. So that's cotangent of theta squared, which should be written like this. Okay? And then finally, 1 over sine squared theta is going to be cosecant squared theta. So this is the third version of the Pythagorean identity that we'll use on multiplications. So what do we really use this for? Okay, and that's this is important, and one of it is to prove that certain trig expressions are equivalent to other trig expressions. Okay, so here's an example for you. All right, so I'm gonna write all 3 of these in the corner so we have them. So 1, we have the traditional Pythagorean identity. Excuse me, I lost something. I hate when I always lose something. Run back, boom, and boom. Alright, so back to the drawing board. Let's see here. So we end up having 1 is sine squared theta plus cosine squared theta equals 1. The other version was, what was the other version? 1 plus tangent squared theta equals secant squared theta. And the last one is when we divide everything by cosine, we end up getting cotangent for everything. So these are 3 versions of the Pythagorean identity. Same thing. I only keep this one in mind, and anytime I need it, I just divide out by what I need. Okay, because everything else is so hard for me to remember. Alright, so here's the problem, and this is what 7.1's homework talks about, and it's show that secant of theta divided by cosecant of theta equals tangent of theta. Now, I know you see an equal sign staring in your face, but note, this is not an equation. Okay? What I mean is not an equation. Because even though you see an equal sign, you're trying to show that the left side is equal to the right side. So it really is a question mark here. That's not really an equation. So what you got to do is you have to manipulate one side, not crossing over ever. Manipulate one side and try to turn it into the other side. So what's the easiest way to do this? Well, you just use the definitions. You know what secant, cosecant is, and you know what tangent is. Okay, we're just working one side, and this is a good strategy. I always work one side until I get totally stuck. And then, I draw this brick wall here so I don't cross over back and forth. Okay, I want to stay on one side and do my work. So I'm going to work this to death. And then, after I get to a point and I think I'm stuck and I don't know where else to go, then I will work this side if I needed to. And then it'll meet up at the bottom somewhere. And then I know that's the path to take to get back to the other side. Kind of makes sense, right? So let's do an example. I know all the scribbles didn't help. So here we go. Secant of theta over cosecant of theta, and we're trying to show somewhere down the rabbit hole this is equal to tangent of theta. Notice how far away I wrote it. So what do we know about secant of theta? Okay, secant is 1 over the cosine or the sine, guys. Which one? I think it's the cosine. And then cosecant is 1 over the sine of theta. Now here's a very helpful hint with this. Okay, usually if you turn everything into sines and cosines, it usually kind of figures itself out. But you'll get a better feel as you do problems with this. So this is 1 over cosine of theta times sine over theta over 1, which that sine of theta, oh, you didn't even have to muscle it too hard, over cosine of theta, which automatically gives you tangent of theta. So you've shown that this is equal to that. Notice we didn't touch the other side. We just pushed to one side to get there. Okay? That's so this is not really that bad. But the big thing here is that this is not an equation. All right. So let's get a more involved example. Show that 1 minus tangent of theta cosine of theta over cosecant of theta. I want to show that this is equal to cosine squared theta. So if this is my paper, this is how you should draw it. Draw a line down the center and don't cross over. Okay? So how are we going to deal with this? Well, you got to have a little bit of a mentality. And what I mean by a little bit of a mentality is you got to try to find ways. So notice on this side, you got something squared, right? On this side, you don't have anything squared. You have 1 minus some stuff. There's two things over here. This side only has one thing. So I'm going to start with the side that has more things to play with. No, the right side is not really too convincing on where I need to go. So on the left side, notice I have cosines. Only cosines on my right side. So I probably need to turn the left side into nothing but cosine. So let's see where I get. Well, tangent is sine over cosine, right? So this ends up being, if you look at just your numerator, you get sine of theta over cosine of theta. That was tangent times cosine of theta over cosecant. Cosecant, that's 1 over the sine of theta. Okay? So now, if you notice your numerator, this and this will factor out, giving you 1 minus sine in my numerator. My denominator is 1 over sine of theta. Well, check this out. Multiply by the reciprocal, you get 1 over sine squared theta. Now, this looks really funny, doesn't it? Recall the Pythagorean identity, that sine squared theta plus cosine squared theta equals 1. So you see the sine squared? See that? I see one right here. So let's solve for sine squared. So this means sine squared theta equals 1 minus cosine squared theta. Okay, and this is why you use Pythagorean identities. Anywhere I see a sine squared theta, I could put a 1 minus cosine squared theta. So this is 1 minus cosine squared theta. Alright, keep solving. We end up getting 1 minus 1 plus cosine squared theta. These cancel, and then finally you're just left with cosine squared theta, which is what we needed. And we are proven. Very, very easy. Okay, guys? So the more and more of these you'll do, the more familiar you'll get. And I always feel that you can never have enough practice, okay? So in the book, I suggested quite a few problems that you guys should work through. If you have any questions, come talk to me. And I will do a few more of these examples in class. So take a look at the video. And remember, in order to grow and in order to accomplish things we've never thought we'd be able to do, you got to be prepared to do stuff that you're not necessarily used to. So